Welcome to this installment of Availability Workbench Helpful Hints. This month's video is about optimizing inspection or condition monitoring intervals. This video will discuss why condition monitoring is a valuable part of a successful maintenance strategy and how to use the interval optimization module to pick the best interval. Studies on aircraft components during the 1960s and 1970s showed that the current methods of managing their maintenance programs were ineffective. The prevailing theory was that all components wore out and that time-based replacements and overhauls would effectively prevent failures. It turned out that only about 11% of the components suffered a wear-out mechanism. The other 89% had the three failure shapes shown here. None of these items would benefit from time-based replacement or overhaul. The dominant failure shape was infant failures. Replacing them on a hard time basis would induce failures into the system. The team that created reliability-centered maintenance during the 1970s concluded that significant advancements in maintenance effectiveness would require expanded use of diagnostic or condition monitoring methods. The effectiveness of condition monitoring depends on three factors. It must be possible to detect reduced failure resistance for a specific failure mode. It must be possible to define a potential failure condition that can be detected by a specific task. And third, there must be a reasonably consistent age interval between the time of potential failure and the time of functional failure. This is known as the P to F interval. Whenever an on-condition task is applicable, it is the most desirable task, since it is usually the lowest cost alternative. Condition monitoring programs are only effective if the P to F interval is sufficiently long for planning, scheduling, and performing a corrective maintenance task to remove the potential failure from the system before it reaches functional failure. Effectiveness therefore depends on the planning and scheduling capabilities of the organization. Let's now switch over to how to do this task. We'll look at entering the corrective maintenance, the preventive maintenance that will be disabled so that it can be performed when the condition monitoring task finds the potential failure. We'll enter the condition monitoring information and then run some optimization scenarios. We have set up a small model for this demonstration with one failure mode for a bearing in an electric motor. The bearing has a characteristic life of 43,800 hours and suffers random failures. The system lifetime is set for 20 years and the number of simulations is set to 1,000. There is one effect for system downtime with a cost rate of $50,000 per hour and one safety effect with a severity ranking of 100 per occurrence. Spare electric motors cost $4,000 and the motor is replaced whenever a failure occurs or a potential failure is detected. Let's take a look at the maintenance task. First, we'll look at the corrective maintenance. Remember, we said the motor is replaced whenever the failure occurs. The task takes about 4 hours to complete, and there's a 2-hour time to ramp down and ramp back up and get into full production, for a total downtime of 6 hours. The mechanics or the multi-craft technicians that we're using, and we'll take 2 of those, and they'll be there for about 4 hours for the task duration. And we need the spare motor in order to do the task. A preventive maintenance task has been set up, but not enabled. And for that task, we're giving a 25% credit on the task duration because of having a planned and scheduled job that typically results in a lot less direct maintenance time. We still need 2 multi-craft technicians at $100 per hour per piece. And we still need the electric motor. Notice also that we have set the ramp time to 0. We're making the assumption that this PM task, when it is done, would be done with many other tasks that are being done in the organization. So the ramp time would only apply to the shut down for the overall PM schedule. Now that we've looked at the preventive maintenance task, let's take a look at the inspection task or condition monitoring task that we want to use. For this task, we've enabled the task at 730 hours. Later, we're going to optimize that task to look at maybe a better interval, and then we'll compare this interval to that one. We say the task duration is about 0.2 hours. There have been a lot of advancements in condition monitoring technology over the last few years, and those advancements have made the analyst a lot more efficient. So it takes less time now than it used to get the data they need. And we're going to use a vibration analyst at a cost of $150 per hour. For the predictive data, there are 4 distributions we could use. You're going to want to use the distribution that makes the most sense in your case for whatever technology or inspection method you're using. In this case, we're going to use a step function just for ease of use. We've set a P2F interval of 2,190 hours with a detection probability of 90% or 0.9. You're going to want to talk with your technicians to find out what are the best numbers to use for the P2F interval and the detection probability. So you're going to want to know how many times in the past they've been able to detect this particular fault and whether or not you've had time to do something about it before you've had a failure. Today we talked about the importance of condition monitoring in a maintenance strategy. And we talked about optimizing condition monitoring intervals using the optimization routine in RCMCost. Thank you for watching our video. Please contact Isograph by visiting their website or calling Brett Peterson at 801-610-0045.